Okay, this is Dr. Mitchell again, and we're going to walk through how to do a chi-square, a one-way chi-square, using JASP. And again, we are going to start in our Excel file here. And this one you'll notice is blank because I'm actually going to walk through how we input the data for this, because this analysis is going to be a little bit different than the way we have entered data for t-tests and ANOVAs and correlations, regressions, analyses like those. So we're going to start out with an example, and in this example we are going to roll a die 100 times. So we can agree that that die has 6 options, right? So when we roll that die, and we're just going to put die roll right here, there are 6 options for it to land, right? It can land on a 1. I'll write out 1. It can land on a 2, obviously. It can land on a 3. You get, I think, where this is going. A 4, a 5, and a 6. So all of those are options. Now, let's say in this scenario, I roll a die 100 times. And in that 100 times, and I'm going to call that count. Right? In that 100 times, let's say 15 of those are 1. All right? Let's say in those 100 times, 15 of those are a 2. Let's say in those 100 times, 25 of them are a 3. Let's say in that, let's say 18 of them are a 4. Let's say in that 16 of those are a 5. And then last but not least, 6 of those are an 11. And so if we look at that, the sum of that is 100. So there's our 100 rolls. Okay. Now again, this is what we actually found. That's not expected. I mean, in theory, in a normal die, we should have equal 1 and equals 2, 3, 4. Those numbers should be the same. Now, in reality, that probably wouldn't happen. But our question now is the frequency that we found these dice rolls, are they different than what we would expect? Okay, well, I'm going to then take this file. I'm going to save it. I'll go to File, Save As, do what we've done before. And I'm then going to go to JASP. And I am going to open that file. So let's go to File, Open, and I'm going to go to where it is on my computer here. Have it in my data sets right there. So there we go. So there's our data. Now, again, this is unique because we don't have each row being an individual subject like we have before. Each row is the die, the variable here, and the options of the variable, and then count is the frequency, the number of subjects, number of samples that fell in that. So in order to do this analysis, we're going to go to frequencies. We're going to click on frequencies and go down to multinomial test. And then this is what it's going to pop up for. So basically what it wants to know is, okay, what is the factor here? What is I'll say repeating, but the variable that you're looking to see here? Well, that's a die, right? It's got 6 options, it's got factors. So we're going to put that in factor. Okay. And then it wants to know count. Okay, so what are the values in each of those? Well, I just happen to call it count, so that's going to be really easy. Count right there. And you'll notice immediately on my right panel here, it performed the chi-square with 5 degrees of freedom because we have 6 options. So 6 minus 1 is 5. And it gave me a p-value. And that p-value is 0.255. So what that's saying is that value is greater than 0.05. So there is not a statistically significant variance in frequencies from our dice rolls compared to what we would normally expect. Okay. Now, there's some other things we can do here if we want. One of those, which is helpful, would be to enter in our own expectation of dice rolls. Okay. So let's say in a normal situation, we would expect each of these dice rolls to occur equal amount of times, right? So So if we rolled them 6 times, as we look at our expected proportions here, we would expect 1, 5, 1, 4, 1, 2, 1, you get the idea, 1 of everything. But let's say that's not what we would expect. Let's say we loaded the dice. We intentionally loaded the dice. I don't know how you do that. And let's say in our intentionally loaded dice, our expected frequencies, and again, this is a scenario, right? There are times in some areas where we don't expect frequencies to equal. So let's say in this die, we actually expected, because we hacked into the die, we actually expected that 6 should have appeared, if we rolled it 3 times more than that, and then maybe a 5 should have rolled, I'm going to 5 2 times more. All right, so there's my expected frequency. Well, now you'll notice in my panel, whoa, now this is statistically significant, right? And all I did was change the expected frequency. Now with a normal distribution, a normal equal proportions of frequencies, this was not significant. But as soon as I told it, hey, actually, we expect a 6 to occur 3 times more often than the other die, the 5 to occur 2 times more often. Well, if you compare our measured values to that frequencies, well, now it's statistically significant. Okay. So that can be really helpful. I can put in some other things here if I want. It'll show me, for example, I can do a descriptive plot if I'd like, and that'll have the plot appear down here. Let me move my picture. With my error bars as well, so that might be helpful for something you're doing. We can also do some confidence intervals, some descriptive data down here. This gives us the observed percentage of each of these. So in the observed, 5 occurred 0.16 or 16% of the time. A 4 occurred 0.18 or 18% of the time. That might be helpful if I want to know what those percentages are, and then there's expected percentages based on what I just told it. So there's some other things here this will tell you if you need those in your analysis. Okay, so that is how we do a one-way factor, a one-way chi-square in JASP. Hope that helped, and we'll see you in the next video.